Thank you for having me give a talk. Sorry I'm kind of late. I had to teach and then I got on an airplane and I've been awake for 36 hours, so if nothing is coherent, now you know why. So I was going to talk about strontium ruthenate. There's been some recent, this is an old problem, 25 years. We had the celebration this summer in Zurich. But there's been recent NMR data that's kind of thrown this whole thing for a loop. So we have our own perspective on this using ultrasound, which I'll talk about. A lot of the work, all the work, was done by my student Chiral, who's a third-year PhD student at Cornell. First student to join my group. He's still there. He hasn't quit, so that's good. And crystals come from Clifford Hicks, Andy McKenzie, the Max Planck group. So it's a question of where are the P-wave superconductors? If you're not a superconducting person, I'll give you a small introduction to superconductivity and why we care. Not superconductivity, but the different symmetries of order parameters. So you know about S-wave superconductors. These are elemental superconductors, things like mercury, lead, and niobium. Some iron pnictides. I didn't want to get this wrong because last time I worked on pnictides was 2011, and I remember it was anyway. Is this still true? Because I knew you would be here and I didn't. Let's skip it for the moment. S-wave superconductors.
True, at least in some place.
Perfect. I'm glad and that's why I put some. So under all the crystal point group symmetry operations of the lattice, the gap structure is invariant. So if you rotate this thing around, even though there's a different sign on these different pockets, if you rotate the square, reflect around any of the mirrors, you get the same thing. This is different than a D-wave superconductor, where your Cooper pairs have angular momentum 2. This is things like cuprates, organics, heavy fermions, maybe some other pnictides. It's only really known, the only real experiment that really did this was Sui and Kirtley when they did the tricrystal junction experiment. That really showed, there are lots of other experiments that indicate D-wave in a lot of materials, but that really proved that the phase actually changes as you go around. So in a D-wave superconductor, if you rotate by 90 degrees, your phase changes sign. So this is quite different. A P-wave superconductor would have, if you just draw a picture of a p orbital, there's a lot of different P-wave superconductors, but if you just draw a p orbital, it would have a single change the phase sign as you go around. And we don't really have any examples. We have helium-3, which is a P-wave superconductor, but it's not a superconductor. It's BCS pairing, but it's superfluid. So we'd really like to have, a charged solid state system. And I'll tell you why we might actually want that, why it's interesting. Part of the question is, in a cartoon level, can Cooper pairs have a spin? So what I mean by that is, if you think about an S-wave superconductor, you have orbitally symmetric pairing. So this is completely in L equals 0. This is invariant under any kind of rotation. And so to have an odd fermionic wave function, you need a spin antisymmetric. So you need spin singlet. You have to pair spin up and spin down electrons, opposite sides of the Fermi surface, into a spin singlet state with total spin 0. So there's no spin left over anymore in the Cooper pair, in some sense. This is all cartoon level. D-wave superconductors, now we've jumped up to L equals 2 from L equals 0. Now your Cooper pairs have angular momentum. You go around the Fermi surface, your gap changes sign twice, but it's still symmetric under exchange. And so you still require a spin antisymmetric wave function, which is still spin singlet. So D-wave and S-wave superconductors are both spin singlet superconductors where the electrons pair spin up and spin down. All of this language is ignoring spin orbit coupling, which is fine for most of the materials. Not all of them. So the question of course, not all of them, and probably not strontium ruthenate. Where the P-wave superconductors, what you're asking for is an orbitally antisymmetric wave function, which means you want a spin symmetric wave function, which means you want one of the spin triplet states, which means your Cooper pairs are a spin 1 object. So you have, in some sense, a little ferromagnetic object in your superconductor. At some very hand-waving level, these two things don't go together usually very well. So for energetic reasons, this is not usually very favorable in any material. It's nowhere nearby, at least in any kind of weak coupling ground state for most materials. The best candidate to date has been strontium ruthenate. And there's a bunch of evidence. I'm not going to go into all the different pieces of evidence that have emerged over 25 years. But one of the first pieces of evidence that came about was the fact that it's not a superconductor even with 2 microohm centimeter residual resistivity. Now, I don't know how many people here know about metals, but if you're a metals person, that's a really clean metal. And it wasn't until they get that down to a few tens of hundreds of nano-ohm centimeters that you really reach the maximum bulk TC. This is a crazy sensitivity to disorder. And there's reasons that P-wave superconductor, because of the way at least for this particular one, the way the gap structure occurs, that they're particularly sensitive to disorder. There were a few other reasons where a lot of the Fermi liquid parameters look kind of hand-wavingly like the Fermi liquid parameters in helium-3. So it was put forward that maybe this could be a P-wave superconductor. And the big piece, oh, yeah, am I going to get to that? Hold on. Huh. Yeah, I will. Okay, good. That's the important part. So why do we care? That's also important. So in a tetragonal crystal, where actually most of those superconductor cuprates, pnictides examples lived, P-wave superconductors, there's actually 2 distinct components to the representation that forms the superconducting order parameter that has a gap along a different direction in space. So this is different than dx squared minus y squared, because even if you look at the opposite phase of that one, the nodes are still running along the diagonal. This one has a node running that way, this one has a node running that way. And what it means is you can form a chiral superposition of these 2 things. Those are 2 degenerate states. And so there are different ordered states for a P-wave superconductor. You could just order as this, you could just order as this, you could also order as some chiral superposition of the 2. And that leads to a time reversal symmetry breaking superconducting ground state that's fully gapped because you've added something with a node plus something out of phase that has a node rotated by 90 degrees. You end up with no node. You end up with a fully gapped superconductor. This is Clifford Hicks' picture of what the superconducting phase might look like on the strontium ruthenate Fermi surface. It's a beautiful rainbow of phase changing everywhere on the Fermi surface, not just across some diagonals, but it changes continuously. And this is really at the heart of why it might be so disorder sensitive, because if you scatter from anywhere to anywhere, you break a pair because you go to a different phase. Whereas an S-wave superconductor, the phase is everywhere. So lead tin solder is a perfectly good superconductor, just like lead. It doesn't care. That was Anderson. The big piece of evidence that came out for spin triplet superconductivity was the lack of a night shift at TC. So in a normal superconductor, vanadium-3 silicide, for example, this is just the example they gave, you measure, so the night shift is sort of a measurement of the local spin susceptibility. And so the idea is if your Cooper pair is formed of a spin singlet versus a spin triplet object, something very different is happening to the spin, something very different should happen to the spin susceptibility. And in helium-3A phase is complicated, helium-3B phase, at least when you go into the superconducting state, you get no change in the spin susceptibility. A regular superconductor gets a change in the spin susceptibility because you pair up, spin down, and you no longer have a spin associated with your Cooper pairs. Strontium ruthenate, much like helium-3B phase, when they measured through the superconducting transition, they didn't see a night shift, which told them maybe the Cooper pairs formed in a spin triplet state, so there's still a spin around, so you still have the same amount of spin susceptibility. There's a formal argument associated with that, but that's the cartoon version. And that stood since 2001 until Stuart Brown noticed when he was trying to measure a different NMR quantity, T2, I think he was trying to measure T2, T something, T1 or T2, he noticed that it looked an awful lot like normal state strontium ruthenate, even when he was below the TC of the material. And the only way you can do that is if you, what's that?
I don't think it was historically exactly that way, but it doesn't matter.
That's what he told me. He was trying to measure T2 and he noticed it looked...
Under strain. I think the first notice is under strain.
Under strain, that's right.
And only way later they revisited.
Okay,
sample.
okay. That's true, yeah.
So before they thought that symmetry changes with strain.
That's right. Right, that's right. That's right. The point is here, what's on the x-axis here is microwave power. So if you've done an NMR experiment, nuclei don't give off a lot of signal, so you blast them with microwaves, and you hope that you get a signal back. And in this case, he's turning down the microwave power, looking at the night shift, and below 10⁻⁶ joules in whatever unit that really means. he gets a night shift again. So it means they were heating up their sample. Actually, Stewart, it's not the first time Stewart's discovered that this has happened. He did this in one of the organic superconductors as well, I don't know, 10 years ago or something like that. So this is actually technically extremely difficult. It's not just a smaller signal. If you know NMR, you're trying to tip the nuclei. You're not getting a 90-degree tip. Now you're getting some 6-degree tilt angle or something like this. So this is a technically very impressive bit of work that he's done. Takes, yeah.
I know he blamed it on a heating, but this happens actually in any system that has spin-orbit coupling enhancement in heavy fermions.
Mm-hmm.
You know this famous 115, cerium cobalt indium 5.
Yeah.
The effects are astonishing. So there is actually very important physics in this. This is not artifact of NMR. It's the fact that, heating, with the RF, it's not as simple as that.
It's not heating?
Well, it's because there is actually a very tricky interaction, spin-orbit coupling and stuff like that, non-linear spin dynamics in the system.
Can it not?
It's not just the heating effect, and that's what we've seen and showed that your electrons appear as if they're heated up.
Yeah.
Okay?
Okay.
Like you do the measurement at 20 millikelvin, you cannot measure these relaxation rates because electrons, really there's a very weird nonlinear dynamics.
Okay.
And we've seen that in these heavy fermion systems.
Yeah.
So there's nothing wrong with the experiment, but I'm just saying it's not like, hey, this is some kind of artifact of NMR and somebody else did the experiment wrong. It's a very delicate.
No, I understand.
And there's a lot of physics in this that it would be nice to have actually theories to help us. It's a problem of basically Abraham's book of nuclear magnetism.
Yeah.
So
I think you should move on.
Yeah.
Also, there were also more papers on that trying to elucidate specific mechanism of this energy absorption, but I don't think it's relevant for this talk.
Probably not. Okay, but I'd like to hear more about that later. So what can be done to probe the orbital symmetry? I mean, if you didn't think about it too hard, you might think, well, S-wave superconductor doesn't break any spatial symmetries. A D-wave superconductor breaks rotational symmetry. It's a nematic in some kind of sense. There's two different possible D-wave states. Usually this is the one that actually forms. P-wave, there's actually a lot of very complicated different ways it can order that break spatial and time reversal symmetry in different ways. You might hope to be able to do some kind of measurement that can just pick up what point group symmetries are broken when we go into the superconducting phase. That's not that easy, but that's what you might hope. So if you want to probe what kind of symmetry is broken when you go into an ordered state, the most direct thing you can do is find a field that has the same symmetry as the order parameter and look at the susceptibility diverge at the transition. So here's a transverse field Ising model where you have some transverse, anything you want, some transverse field down here. And so you go from an ordered ferromagnetic state into a disordered paramagnetic state as a function of some tuning parameter. And you could measure as a function of temperature a diverging ferromagnetic susceptibility. This wouldn't work in an antiferromagnet, but if you used a neutron, which is an antiferromagnetic field, if you look at pi, you would also see a diverging susceptibility. So this has been done for broken rotational symmetry in the iron pnictides. Iron pnictides have a tendency, this is not the Fermi surface, this is a cartoon of a Fermi surface, have a tendency to want to do maybe some kind of Pomeranchuk distortion, maybe, or something else along the diagonal. It's not that simple. We'll just use this cartoon. And so you could imagine that maybe if you apply a strain to the crystal that's of the same symmetry as its desire to distort its Fermi surface, you might be able to couple into that very strongly and see a diverging susceptibility. And that's exactly what Ian Fisher's group did. They did elastoresistivity, where they take the sample and they pull on it a little bit along this diagonal direction, and they measure the change in the resistivity. And across the phase diagram, as they come towards the critical point where the nematic phase transition temperature goes to 0, they see that this nematic susceptibility diverges very strongly.
But that's nematic, that's not superconductivity.
Absolutely. This is nematic. This is a structural phase. It's a fancy word. Yeah. So the problem is superconductors also break gauge symmetry. So you can't do this. You can't just put orthorhombic strain on your crystal and expect to directly couple into the superconducting order parameter because it breaks other symmetries. So what it means is there's no linear coupling. So what we do is we just throw everything we can at it, which is sound. Sound is, so strain is actually, so it's a second rank tensor, which means there's a lot of different representations of strain in the crystal. So in a tetragonal crystal, there's 2 scalar representations, compressions, and there's 3 shear representations, so 3 different ways you can shear a tetragonal crystal. And that means there's a lot of different strain fields in the crystal that could couple into a symmetry breaking at a phase transition in a different way. And that's what we're going to use to look for P wave, or specifically 2-component superconductivity versus 1 component. Just so you have it in your mind, this is a compression. A compression is something that changes the size of the crystal, and a shear is something that preserves the size but distorts the symmetry. The physical experiment that we do is something called resonant ultrasound spectroscopy. So we take a very small crystal, we hold it in between 2 piezoelectric transducers, and so a 3-dimensional crystal then oscillates at some resonant frequency. This is just wave on a string in 1 dimension translated up into 3 dimensions. And so you get more complicated looking resonances and a more complicated looking resonance spectrum, but this is classical mechanics. So what we can do is we can take our system, we can change the frequency, we can find all of these resonances, we can solve the elastic wave equation, and we can turn this back into all of the elastic constants or all of the speeds of sounds if you want. So we can get the full strain susceptibility tensor for all possible strains in 1 experiment. Now, this looks like a very complicated strain pattern. This is my student made this in, I don't know, ComSol or something like this. So this is what our sample is actually doing at a particular frequency. It's flexing and twisting and buckling in some very colorful way. You might think that there's not a lot of hope for getting information out of that, but this is where group theory comes to the rescue. So you can always decompose any arbitrarily complicated strain pattern into the 5 irreducible representations of strain modulated at some finite wavelength in your crystal. So there's 2 compressions. There's only 2 ways you can compress a tetragonal lattice. You can squish the in-plane size, or you can squish it along the c-axis. And there's 3 ways you can shear it. You can do what would be a B1G shear. This is like the orthorhombicity in YBCO. This is like the orthorhombicity in the pnictides. That's a C66 shear or a B2G shear. And then C44, you can shear it along the c-axis. And this is actually a 2-dimensional representation. There's 2 unique components to that representation. So with that, because this is only a 20-minute talk, I'm going to skip over, we can extract physics that only couple. So for example, if you measured the iron pnictides, the elastic constants associated with these strains, which I've written up here, would do nothing, 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 and then something towards the nematic phase transition. So you could see what's actually got the action in it and what doesn't. As far as superconductors go, superconductors all show discontinuities, so drops in their scalar elastic constant. So I keep using different words for this. These are, you could think of it as the bulk modulus, but now there's 2 of them because it's tetragonal. It's the A1G elastic moduli, the compressions. Whenever you apply a compressional strain to the crystal and measure the elastic constant and go through a superconducting transition, you're required to have a discontinuity. That's not up for negotiations. This is, if it's a second order phase transition, this is the same reason you get a jump in the specific heat. Actually, if you flip this upside down and multiply it by dTcd pressure, you will get quantitatively the jump in the heat capacity. That's Ehrenfest relations. So all superconductors, if they're second order phase transition, you get a drop down in the elastic constant at the phase transition in the compressional elastic constants. Why does this happen? This happens because of the way, so elastic constants, what we're actually measuring is this, like Kim was measuring the second derivative of free energy with respect to angle of the field. We're measuring second derivative of free energy with respect to strain. And so if you want to write down a free energy is just a number, it's a scalar, A1G representation, which means all the terms you write in your free energy have to respect that. So this is Hooke's law, this is elastic constant times strain squared. This is your standard Landau expansion around phase transition. So there's the order parameter squared. There's something to keep it positive, definite, or whatever out at high order parameter. And then there's a coupling term. So you can couple your strain, which is just this thing, it's me squishing the crystal. You can couple it to the square of the order parameter for any superconducting order parameter. You square the order parameter, you get rid of gauge symmetry breaking or any other symmetries it breaks, and you just end up with maybe something like the superfluid density. And so you can work through the Landau mean field theory, and you find that above the phase transition, you get some bare value of the elastic constant, and when you go below the phase transition, you get a drop that's related to some combination of these constants. You can find this, you can work through the same thing for heat capacity if you want. It's the same thing, just with some different coefficients. But what this requires is that I've taken the square of the superconducting order parameter, I've coupled in strain to the first power. That means I can only do this with A1G strains because I need my free energy to be A1G. If I try and put a shear strain in there, I can't do it. I would have to square it, and that's a very weak coupling. That's strain squared, order parameter squared. So that's why only the compressional moduli show this jump at the transition. So
Also, A1G Raman mode should show the same behavior.
presumably, yeah. Yeah, that's right. Yeah. Do they?
I think they do.
Yeah,
It's
okay.
just very, very weak effect.
Very weak, yeah.
I only see that so coherent excitation of displaced fixation of coherent.
Yeah. Okay. Okay, that's interesting. We should talk about that actually. So we do this in strontium ruthenate. The challenge is TC is extremely small, and the the size of this jump goes something like TC over T Fermi squared, and T Fermi is a gigantic number in strontium ruthenate. TC is a very small number. This jump is small. So my student worked very hard and built a new way of doing resonant ultrasound, which unfortunately I don't get to talk about. But we've got really high precision elastic constants, and for the first time we've actually measured the jump in the compressional moduli through the phase transition. There's two compressional moduli, and because they have the same symmetry, there's a coupling constant between them. And just so that we know we're not crazy, this jump times this jump should be this jump squared, and it is. So 4 minutes, perfect, we're almost done. So we think we can at least measure the thing that has to be there for all superconducting phase transitions, so we know we're at least doing something right. So now, what makes two-component order parameters interesting? Remember, it's a p-wave superconductor. There was two degenerate ways, you get two degenerate p orbitals in the state. What this means is this actually forms an EU representation in the D4H symmetry group. So in a tetragonal crystal, you can have your p orbital like that or like that, and they kind of form a two-dimensional little object. And when you go to form bilinears to put in your free energy to find out what happens to your elastic constants, you can, of course, take the length of that little vector. So here's your, I've just called it eta. This is superconducting order parameter. It's got two components. So you can square both components, basically take the length of that vector. That's similar to squaring the superconducting order parameter like we did before. It gives you an A1G. But the thing is, you can form other bilinears when you have two components, because you can form eta x squared minus eta y squared. And that doesn't transform like a scalar. That transforms like a B1G. This looks like dx squared minus y squared. And you can form eta x times eta y. So there's a B2G bilinear. This means there's more complicated bilinears that have non-trivial representations that you can form if you start with a two-component superconducting order parameter. You can't get this from D wave or S wave.
No,
you can if it's dx dyz, yeah, but from the simple standard dx squared minus y squared, you can't get this. So what this means is, right, this is just saying there's new couplings in your free energy. So for a standard D-wave superconducting order parameter, your A1G strain, which is this guy, couples to the square of your superconducting order parameter. That's what we talked about before. That's fine. But your B1G strain, as I told you before, can't couple to the square of your superconducting order parameter because that doesn't respect the symmetry of the free energy, which is just A1G. Can't do that here. But here, you can form a bilinear that's B1G, and you can multiply by a B1G strain, and that gives you back a scalar. So that's a term you can put in your free energy. And you can do the same thing here. So now you have two other linear in strain, bilinear in order parameter terms in your free energy, and now when you go through the superconducting transition, you might expect something to happen to the elastic constants that govern this strain and govern that strain. So here's the punchline. We measured the shear moduli through TC in strontium ruthenate. C44 is a c-axis shear. It's not allowed to do anything except have a change in slope at the phase transition, and that's the purple one, and that's what it does. It just goes to the phase transition and has a change in slope. I can explain all the wiggles and stuff like that. That's the way we decompose the data. But C66, so this is the same B2G symmetry of the nematicity in the pnictides, for example. It's taking the square and distorting it into a diamond. That one actually has a jump of about, I guess it's 100 parts per million, which is a pretty big jump. So as you go through the phase transition, it looks like what we saw on the scalar elastic moduli, which you normally always see. This one also shows a jump. Now I should just, for clarification, this was actually reported in Christian Lupien's thesis from Louis Taillefer's group in a long time ago, I don't know, 2000 and something. Never published, but has been known about, which is what motivated us to do the experiment. The difference here is they weren't able to do for technical reasons, the way they're doing the experiment, they couldn't do the A1G elastic moduli. So they were not able to really know whether this was pure C66 or whether they're mixing in other, it basically means how square you can cut your crystal. We don't have that problem because we're doing a different technique. We have other problems, but we don't have that problem. C11 minus C12 is actually interesting. You can ask me about it. All of these elastic constants are measured at the exact same time. So it's not like this one just has a jump, but it's shifted because, I don't know, I have some lag in my temperature different between the two different experiments. This is really, it's going through the transition, doing nothing, and then it starts to drop below the transition. This is probably related to the fact that the ultrasonic attenuation for this channel is massively larger than anything I've ever seen in any other material. So it's like, it looks like some disordered mess. It just sucks sound out of the system like crazy. And Christian Lupien also saw this. So it's actually, to do thermodynamics, elastic constants, you have to actually do these experiments slowly. And it's actually hard to go to low enough frequency. Even at a megahertz, it's not really slow enough to actually do proper thermodynamics. So this is showing a drop basically due to Kramer's Kronig. It's being forced to change because the attenuation's changing so much. Bunch of details. We don't really know the answer, but certainly C66 shows a jump, and what that means is it has to be a two-component superconducting order parameter. There's actually a couple other more complicated ways you can get out of this, but there's two p-wave representations, the normal kx, ky, which you hear about as px plus ipy, the chiral superconducting state. You can ask me about that. There's actually a d-wave superconducting state, which is dxz, dyz, which is, cartoon picture is there's pairing with a node in the kz equals 0 plane, so that means you're pairing electrons in different planes, which is weird in a very two-dimensional material, but maybe not impossible. Attenuation's interesting, you can ask me about that. That's all. So we see self-consistent discontinuities in the compressional moduli at TC. We see a discontinuity in C66. Really, there's only two consistent ways you can do this, and the attenuation is actually really complicated and interesting. That's all I have time for. Thanks.
5 minutes